Hi guys, in this video we are going to learn a line clipping algorithm called Cyrus beck line clipping algorithm. The goal of this algorithm is same as other line clipping algorithms. You have a line here, the line is P0, P1 and you have a clipping window. This blue rectangle is your clipping window. Then you have to flip the line, or you have to find out the visible portion of the line with respect to this clipping window. So this Cyrus beck line clipping algorithm is something different than Cohen-Sutherland line clipping algorithm. It actually uses the parametric representation of the line to execute the algorithmic procedures rather than using Cartesian equations. Just have a deeper look into the line and its equation. The line in concern is P0 to P1. It is the blue one. Then the parametric equation of line can be written as Pt equals to P0 plus T multiplied with P1 minus P0, where the value of T is in between 0 and 1. So now try to find out if this equation is capable of representing the property of line as it is. To understand this, let me explicitly define the coordinates for P0 and P1. Now say the Cartesian coordinates for P0 is x0 and y0, and the Cartesian coordinate for P1 is x1, y1, and t is your parameter. So t is the parameter whose value is in the range from 0 to 1, 0 less than equals to t, less than equals to 1. Now it says that the value of t can be varied in between 0 to 1. So just put the initial value of t in this equation, which represents x values of the line. So if you put 0 in this first equation, x equals to x0 plus x1 minus x0, that means the difference between the x values of starting point and end point, and you have to multiply it with the initial value of t. So what will be the value of x then? x0. That means if in this equation, if you put the initial value of t, then you are getting the initial value of x. Then put the final value of t in this equation, which is actually 1. So if you put 1 in this equation, then what is going to be the value of x? It will be x1. So by putting the final value of t in this equation, you are getting the final value of x. So by varying the value of t in between 0 and 1, you will get intermediary values for x in between x0 and x1. Similarly, if you try the same procedure with the y values, you are going to get the same result. Say we put the initial value of y, t, in the y equation, then you get y equals to y0. Again, if you put the final value of t in this equation, then you are going to get the final value of y, that is y1. So from this discussion, you can conclude that by varying the value of t from 0 to 1, you are going to get each and every point in between p0 and p1. So this is the starting point of Cyrus-Beck line clipping algorithm. Next, how this Cyrus-Beck algorithm actually clips a line. To find that, you need some vector calculations. How? If you carefully observe the line against the edge of the clipping window, you can find that this point P0 is lying outside the clipping window and P1 is lying inside the clipping window. Now, as a goal of the clipping procedure, you have to find this intersection point. This intersection point you have to find out. So say this intersection point is P T I, right? So now to find this PTI, you have to do one thing. You have to assume one outside normal vector to the clipping window edge with respect to which the clipping has to be performed. I repeat it once again. You have to assume one outward normal to the edge in concern. In this case, our edge in concern is the left edge of the clipping window. Then next, you have to assume an arbitrary point PE on the edge in concern. Here it is for this example. Next, what you have to do? You have to find the dot product between this outward normal vector Ni and between the vector Pt to Pi. Hope you have got my point. So I should repeat it once again. What you have to do, if you think it in another way, you can assume a vector from a point Pt on the line which we need to clip to that arbitrarily assumed point Pi on the edge in concern. This is a vector from pi on edge to pt on the line to be clipped. Then from this pt you have to assume a outward normal vector to the edge in concern, right? So this is your ni for this particular point. If you look at this ni, this is basically normal. That means it is making an angle of 90 degrees with the edge in concern, the left edge in our example, and you have another vector from point pe to the point pt on the line which you have to clip. Then just note down the angle between these two vectors. If the angle is theta, this theta is actually greater than 90 degrees for this point. So now find the dot product in between these two vectors. That means find the dot product between ni and pt minus pe. So now tell me, will the value of this dot product is going to be greater than 0, or if it is going to be less than 0, or it is going to be equal to 0? As the angle between the two vectors is greater than 0, the dot product value is going to be less than 0. pt minus pe. That means, as per the definition of dot product, you are multiplying the amplitude of this outward normal vector with the amplitude of this pt minus pe vector, and will multiply with the angle between these two vectors, cos theta. Now, as the value of cos theta in this example is less than 0, as theta is greater than 90 degrees, this value is going to be less than 0. It is going to have a negative value. Next, do the same calculation for a point pt which is inside of your clipping window. Say now point pt is here, so it is your pt minus pe vector. This is your pt. Now again, from this pt you have to assume one outward normal vector with respect to the edge in concern. So this is now your ni, and this vector is your pt minus pe. Now just observe the angle between these two vectors. Now you can see that this angle is less than 90 degrees. If the point is inside your clipping window, the angle between the two vectors is less than 90 degrees. Now in this case, what is going to be the value of this dot product as the angle is less than 90 degrees. The value of this dot product is going to be greater than 0, right? Next, what you have to do the same procedure for the point PT, which is your intersection point. In our example, this is the intersection point. That means now try to calculate the same dot product for the intersection point. In this case, this is your PT minus PE vector, and this is your outward normal vector NI. Now just have a look at the angle between these two vectors. It is actually 90 degrees. So now theta equals to 90 degrees. So now what is going to be the value of the dot product? As the angle between these two vectors is 90 degrees, now the value of the dot product is going to be actually 0, as the value of cos 90 is 0. So if you have followed the discussion until this point, what you can conclude? You can conclude that if you go on calculating the dot product for each and every point PT onto the line with the outward normal vector for the point at which intersection is taking place, the value of this dot product is going to be 0. This is the phenomena which we are going to use in this Cyrus-Beck line clipping algorithm. So if you have not been able to understand what I have discussed until now, just rewind the video a little and carefully listen and jot down what you have understood in your copy for this portion. And once you have been able to understand what I have discussed, then come to this portion. The point PT for which intersection will happen, the following condition will hold, and the condition is Ni multiplied with PT minus PEI. That means an arbitrary point on the edge I will be equal to 0. Now try to simplify this equation. Ni dot multiply dot PT. What is the value of PT? As per the parametric equation which we have discussed some times ago, it is P0 plus T multiplied with P1 minus P0 minus PEI, and this whole value should be equal to 0. Now solve this equation to find the value of the parameter T for which you get the intersection point. That means you have to find the value of T in this PT for which this intersection condition holds. If you solve this, you are going to get something like this: Ni multiplied with P0 minus PEI over minus ni dot p1 minus p0. Now at the next line you can see that we have replaced p1 minus p0 with d, a constant, because p1 minus p0 will always be constant for a line. Why? Because this is the difference between the starting point and end point of the line. So d equals to p1 minus p0. Now think for a while. What will happen if the value of d equals to 0? Just think for a while. I hope you have give it a thought. Now, when the value of d can be 0, if p1 equals to p0, when it will happen? If it is a point. That means if the line is something like this, in this case it is a point. So essentially p1 will be equal to p0. If you think in terms of coordinates, then x1 will be equal to x0, y1 equals to y0. In this case, essentially there is no need to employ a line clipping algorithm, rather employ a point clipping algorithm. So this was the basic idea behind the Cyrus-Beck line clipping algorithm. Now look how this algorithm will work and what are some situations which might arise while executing this algorithm. Here are some situations which might arise during the execution of the algorithm. The line might be outside the clipping window, as it happens in this case, the violet one. You can see that this line is completely outside the clipping window. So you have to formulate something which can handle such situations, because obviously in this case also you can calculate those dot products. Again, the line might be entering or leaving the clipping window in terms of parameter value t. As you are thinking in terms of vectors, you all know that vectors has some kind of direction. So you can think of the line as entering into the clipping window at some point of time and leaving the clipping window at another point of time. If you start from t0, t1, that means you are going to follow the direction from t0 to t1. You will start your calculation from point t0 and proceed towards t1. So when, and again you can see that this line p0 to p1, that means this green one, has actually intersected two edges of the polygon. That means you will find two intersection point with respect to two different edges. So at TL, this point, that means with respect to the left edge, this line is entering into the clipping window. If your direction is from t0 to t equals to 1, and at t subscript t, at this intersection point, this line is actually leaving the clipping window. Again, if your direction of calculation is from this point to this point. So how you can find out when a line is entering into the clipping window and when it is actually leaving? It is again very simple. For potentially entering intersection, PE, that is potentially entering, NI multiplied with D is going to be less than 0. So if you recall the previous discussion, this is actually your D vector. So in this example, this line itself is your D vector. Then with respect to the left edge, this is your outward normal vector Ni. So the dot product between these two vectors is going to be less than 0. So when the line is actually entering into the clipping window, you can conclude that the dot product between the outward normal vector with respect to the edge through which the line is entering into the clipping window with the line itself will be less than 0, and the intersection point which you will find with respect to that edge is going to be your TL. Okay, again, if you look into this example itself, the line is actually leaving the clipping window with respect to this top edge. So if you find the dot product with respect to the outward normal vector from that top edge with the line itself, you will find that the value of dot product is going to be greater than 0 because the angle is less than 90 degrees. So the intersection point with respect to the edge where this leaving phenomena is taking place, you can call it TR. So in this way, you can classify the intersections in terms of intersection with respect to the entering edge and intersection with respect to the leaving edge. Now come to the second case where the line is totally outside the clipping window. In that case, how you can find out that the line is outside the ambit of clipping algorithm? To do that, you can do one thing. Just at first extend the clipping window edges towards infinity. Here we go. Then do this potentially entering and potentially leaving calculation for this line with respect to the edges. So Here in this example, you can find one potentially leaving point with respect to this extended right edge, and you find one potentially entering point with respect to this extended bottom edge. How? As per our calculation, this is our D vector and this is your outward normal vector Ni. So at this point, what happens? The angle becomes less than 90 degrees. So this particular point is potentially leaving point as per our discussion. Potentially leaving intersection point is there where Ni multiplied with D greater than 0 or angle is less than 90 degrees. Again, this is going to be your potentially enter point. So again, what happens? This is your D and just a moment. I should erase this junk from here. And again, assume the outward normal vector Ni with respect to this, well, I don't know, with respect to this bottom edge, and now the angle between these two lines is greater than 90 degrees. So the potentially entering intersection condition takes place here. So you can term this point as potentially entering point. So what actually happens here? You have to find PE max and PEL min for all such potentially entering and potentially leaving points for that particular line. And what is the procedure of calculating this PE max? It will be the maximum of 0 and all the PEs. In our example, this is our PE. So if you find the max between 0 and PE for this line, then your PE max is going to be PE itself. You get only one potentially entering point. Again, you have to find out another variable called PL min, which is the minimum of 1 and all PEs. In this case, it is your PL. So what actually happens here is, if PL min is less than PE max, PL min is less than PE max. If this condition holds, then you can say that this line is totally outside the clipping window. So essentially what you have to do, you have to reject the line. You don't have to apply your clipping algorithm on such lines. Now have a look at the pseudocode of the algorithm itself. At the first line, it is being told that recalculate Ni and select a PEI for each edge. It asks you to calculate Ni for each edge and decide one PEI for each edge I. Then for each line segment to be clipped, here we have two line segments in this example. For each line segment to be clipped, if P1 equals to P0, that means, in other words, if D equals to 0, as we have discussed before, it is actually not a line, then it is a point. So clip as a point, else you have to declare TE equals to 0, TL equals to 1. That means you are initializing your parameter T. Once you have initialized parameters, then for each line you have to follow a particular procedure, an iterative procedure. For each candidate intersection with a clip edge, if ni dot di not equals to 0. So why you are calculating ni dot di and checking it against 0? If ni dot di equals to 0 for a certain edge, then essentially the line will be parallel to that edge. Just look at this example. Let me draw one line. If you look at this line drawn by me, you can see that this line is parallel to this left edge and parallel to this right edge. So if you calculate the dot product between D and Ni with respect to this edge, then the dot product value will be 0. It implies that, or at least you can see it visually also, this line is parallel to this edge. So you cannot clip this line with respect to this edge. You can surely clip it with respect to the top edge or bottom edge, but as this line is parallel to left and right edge, you cannot clip the line against those left and right edges. So before going further, you are rejecting those lines and considering only those lines which don't satisfy this condition. Then you have to calculate T. Use sign of Ni di to categorize as Pe or Pl. That means if you can go back a little, what we have done, we have categorized the lines as potentially entering or potentially leaving candidates using the sign of Ni dot D. If Ni dot D was greater than 0, it meant that it was potentially leaving. If it was less than 0, it implied that it was potentially entering. Then you are checking the condition where the line is totally outside the clipping window by calculating PE max and PL min. Once you have done this, then you check that condition. If enter TE greater than TL, return null. That means the line is totally outside the window. Else you will find the intersection points. So this was the Cyrus-Beck line clipping algorithm for your reference. Now, how you have to use the study material, as I always say, first read the material itself, then watch the video carefully, take notes whenever you think necessary, then again come back to the reading material and read it in between the lines. So here is a reference for this reading material. Hope you enjoyed it. Thank you.